EEE 378 Digital Electronic Tools. I'm Wei Xiang. Today I'm going to show you how to solve question 2 of assignment. This is the question which is divided into part A and part B. Part A. What is propagation delay and hazardous? Hazard is a characteristic of a circuit. A circuit with a hazard may or may not glitch. Glitch is an unwanted pulse that may occur in a circuit with hazard. The state of a circuit and the pattern of input values determines if a circuit with a hazard will cause glitch. Glitch can occur when different paths through a circuit have a different propagation delay. Propagation delay is the time between 50% of the rise time and pause time. From figure 2, there is a propagation delay of NOT gate when inverting the input of I. Due to propagation delay of NOT gate, the output of OR gate will experience an unwanted pulse from 1 to 0 and then to 1 instead of 1 continuously. This unwanted pulse is known as glitch mentioned just now. It is dangerous if logic causes an action where output is unstable. As an analogy, a wet floor is a hazard. However, it is not a problem unless someone slips and falls, which would be a glitch. There are two types of hazard, which are static hazard and dynamic hazard. Static hazard is when the output should remain static but experiences an unwanted pulse. Dynamic hazard is when the output should go through a smooth transition but changes more than once before settling at the new values. It exists when there is 3 or more different paths from one input variable with different propagation delays converging in the circuit. Static hazard occurring when input changes cause the output to go from 1 to 0 and then to 1, which known as static 1 hazard, while 0 to 1 and then to 0 is known as static 0 hazard. Dynamic hazard occurs when input changes cause a double change from 0 to 1, then 0 to 1, or from 1 to 0 and then 1 to 0. Now let's see the example circuit with static 0 hazard and its output waveform in figure 3 and 5 respectively. Initially, A is equal to 0 and B is equal to 1. Hence, the output G1 equal to 0 and G2 equal to 1. At time t1, A changes its state to become 1. So now A is equal to B and equal to 1. The output of gate 1, G1, becomes high after a time delay equal to the propagation delay of AND gate 1. The output of gate 2, G2, goes low after a time delay which is equal to the sum of propagation delays of inverter and the AND gate 2. Hence, output Y goes high for a short duration as shown in figure 5. This short duration high pulse is unwanted and called a static 0 hazard. Next, the figure 4 and 6 are showing the circuit with static 1 hazard and its output waveform. Initially, input A, B, and C are equal to 1. So the initial gate outputs are G1 equal to 1 and G2 equal to 0, with final output Y equal to 1. When the input of B changing from 1 to 0, then the G1 will become 0 and G2 will become 1. The final output Y supposedly remains the same. However, it doesn't. This is because of the propagation delay of NOT gate. The effect of propagation delay of NOT gate is as shown in figure 6. Thus, the output Y goes to 0 momentarily as shown in figure 6 as well. This is called as static 1 hazard. After that, we will see the example circuit of dynamic hazard. From figure 6, there are 3 different paths from Y to F, which are shown clearly with different color of arrow. There is an example gate propagation delay written on each gate, which are AND gate, OR gate, and NOT gate. By this, the propagation delay can be calculated by sum up the delay of each gate it passes through. The dynamic hazard at F results because a change in Y arrives at F from 3 different paths at 3 different times. From the timing diagram as shown in figure 7, there will cause a breach at F while bit Y is changing from 1 to 0. By this, the output of this circuit transitions back to 0 before settling at 1 instead of making a smooth transition from 0 to 1. This is known as dynamic hazard. Part B. Implement the following functions using 3 times 4 times 3 PLA with true and complemented output capability. Step 1. Truth table. The first function is equal to summation of minterm of 0, 1, 2, 5, and 6. The second function is equal to the summation of minterm of 1, 3, 4, and 5. And the last function, which is third function, is equal to the summation of minterm of 3, 4, 6, and 7. By implementing the 3 function into truth table, the truth table is as follows. Each of the minterm for each function is filled as 1 and the rest is just simply filled as 0. The next step is K-map. The first K-map is for first function, where the red color circle is for true output capability and the black color circle is for complemented output capability. The function of F1 is equal to X bar Z bar plus Y Z bar plus Y bar Z, while the F1 bar is equal to YZ plus XY bar Z bar. The second K-map is for the second function, where F2 is equal to X bar Z plus XY bar, while the F2 bar is equal to X bar Z bar plus XY. The last K-map is for the third function, which is F3 equal to x z bar plus y z. While the f3 bar is equal to x bar z bar plus y bar z. Next, the last step is implementation of PLA. From the 6 function obtained from the K-map just now, 3 of the 6 function is chosen, which are f1, f2 bar, and f3 bar. This is because each of the function has a common term where f1, f2 bar, and f3 bar has a common term with x bar, z bar, while f1 and f3 bar has a common term of y bar, z. 3 times 4 times 3 PLA is represented as 3 input, which are x, y, and z, while 4 is represented as 4 number of minterms. And the last number of 3 is represented as the 3 output, which are f1, f2, and f3. This is the implemented PLA for f1, f2, and f3. An XOR gate is used to invert the f1, f2 bar, and f3 bar to get a true output, which is f1 for f1 and f2 for f2 bar and f3 for f3 bar. In order to invert the output from the OR gate, for f1, the second pin of XOR gate is applied to ground, while the f2 bar and f3 bar, the second pin of XOR gate is applied to 5V, which is represented as high, in order to invert the f2 bar and f3 bar become f2 and f3. Thank you.